Welcome back. In this video we are going to show Pythagoras theorem with 64 options of line segments and then to the 256 ways to arrange these lines formed due to cos square theta and sin square theta. Cos square theta generates 16 line segments, sin square theta generates 16 line segments. Now that those things are already described in previous videos, and we have already shown how multiplication glues in 4 different ways. For every trigonometry ratio, 4 different triangles are formed that we have shown with the 4 different symmetries. Here we are trying to show the nature of lines generated due to cos square theta and sin square theta. On the left side we have kept the arrangements of cos square theta. First of all, we don't take trigonometry ratios as pure numbers. We take trigonometry ratios as the transformations of line segments and forming more number of line segments out of one given line segment. We start the trigonometry working with a given line segment, say L, that is a single line, and that is shown in red here, and that is shown as a controller here also in this diagram that we will show like this. The moment we will change it, the whole arrangement changes, and we have already made 219 construction steps that you can download from here. From this link you will get the data of this output. Multiplication is gluing is shown in this YouTube video, which is kept here, and you can download this file from this location. Then you can easily play with this with high graphic windows with bigger screens, such that you can understand everything. For every different angles, that is a seed angle, you can see how the line segments of cos square theta and sin square theta are changing. That will help you to understand the dynamics of these arrangements. We have kept this picture in this way because that helps us understanding the arrangements. Suppose here we have kept a slider. That slider is to bring these two pictures near each other. Suppose this is the arrangements of cos square theta and these are the arrangements of sin square theta. So we have kept two things different. We have made a convention that hypotenuse are drawn in red, bases are drawn in blue, and perpendiculars are drawn in green. So always we will see in our diagrams the hypotenuse are in red, or important circles are drawn to highlight the things in different way. Here you can see 16 line segments, 16 blue deep line segments, and which are all made due to theta. These are all cos square theta line segments, and all line segments have a name in geometrifying trigonometry. All points have a particular naming convention in geometrifying trigonometry, such that we can understand which line segment cuts where, which line segment has what kind of behavior. Here the seed angle is like this, it changes, and due to this arrangement change, the whole arrangements are changing. We are keeping the cos square theta line segments on left side, sin square theta line segments on right side, and when we change the slider, the sin square theta arrangement goes away or comes near. And when we will bring these lines nearer, then we will find a magic here. Like, see here first. Suppose we are taking the angle 47 degree seed angle, so that we can describe it easily. Now we have kept the cos square theta and sin square theta very near, and all the things are coming on a single page. such that we can demonstrate it better. The blue lines are the line segments representing cos square theta, and green lines are representing the line segments for sin square theta. Sometimes they are overlapping and sometimes they are collinear, sometimes they are not collinear. When the blue line and green line are not collinear, they are also cos square theta and sin square theta line segments, but they are not directly addable because they are not collinear. But if we take the numerical value of the lengths, then we will find the length is equal to L square, that is the L is the unit length here, and L square is equal to cos square L into cos square theta plus L into sin whole square theta, and in that way the cos square theta plus sin square theta become 1 and L square remains. So we will get L square when we will take the summation of the lengths of these, because this is the line segment here is the L into cos theta whole square, and the green line here are L into sin theta whole square. So ultimately, it is going to give you the length of L, because we are taking the construction such that L into cos square theta and L into sin square theta, L is taken common and cos square theta plus sin square theta becomes 1. You will get the lengths of this line segment as the cos square theta effect will come here, because this L is drawn with that, and if we take this L as a 1, then it will look easier to understand. But to make it zoomed and to make it more clear, we have kept it a longer value. We can change it with that diagram, that is a controller. We have kept all these things together and we have constructed everything manually here. We can use JavaScript also. And we have kept some JavaScript here for your understanding. Here you will see the global JavaScripts. We can save our time with the JavaScripts also. You can check with this file, then you will get several guidance on JavaScript, and JavaScript works in Geogebra. In Geogebra scripts also work and JavaScript also work. You can use any of these, but JavaScript has more options, so we use JavaScript in more cases. Let me explain you here. That is, this one is LHF. What does that mean? ABCD these four are cos theta symmetries. EFGH are sin theta symmetries. Here we have used H and F. F is also sin theta, H is also sin theta, and H into F is not equal to F into H, because the geometry is not commutative for geometrifying trigonometry. So the order of multiplication is important. This is LBBZ, which is also cos square theta, because B is cos theta, B is cos theta, so multiplied is giving the cos square theta. So all the line segments are not collinear, some are collinear. Suppose here LBAZ is a line segment which is a variety of cos square theta, and LAHZ is a sin, LAH is a cos theta sin theta. In the similar way, LBA is a cos square theta, purely cos square theta. We have taken all the line segments here and we have shown everything. All the line segments are represented here, such that you can cross verify how the nomenclatures are done. The stepwise construction of nomenclatures will be coming in a different video. In one video we have already shown to some extent. In some other videos people are requesting that I have to give some other video where I will explain the naming convention of line segments and points. You can see every point has a name, every line segment has a name. Now we will try to separate out these two pictures. On the left side the blue lines are there, and on the right side the green lines are there, and that means we are trying to show the line segment of cos square theta and sin square theta separately. With that we can identify that which line segments have a possibility to become collinear. Suppose we can see, suppose here if we keep it with a less distance, suppose 0.3, this distance is sufficiently long. If we adjust it with here, suppose if we take it from here, suppose gluing distance is taken as 0.3, then we will see cos square theta line segments and sin square theta line segments are going little offsetted, so that we can show it more clearer. Suppose we are now showing it here, and we can do one more thing also. We can change the seed angle to 20 to 30 degree, then we can see the difference is better, because at 47 degree it is almost square, it is almost looking like square, so it is tough for you to understand. Suppose we are reducing this value to say 20 degree, around 28 degree, okay, then we can see the magic of these alignments of line segments. We have already shown in previous videos that ABCD into ABCD, the Cartesian product, gives us AA, AB, AC, AD, BA, BB, BC, BD, CA, CB, CC, CD, and DA, DB, DC, DD. These 16 type of cos square theta are possible. Now, for sin square theta cases, we know E, F, G, H are varieties of symmetries of sin theta. So E, F, E, G, E, H, here you will find all the line segments. I am just telling you. E, F, E, G, E, H, F, E, F, G, F, H, G, E, G, F, G, 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 H, and H, E. You will get all these line segment H, E, H, F, H, G, H, H. These 16 are sin square theta. Now, all the cos square theta and all the sin square theta are not collinear. Here you can see an interesting geometry. If you check only cos square theta here, see, only cos square theta are kept here, where these are blue like lines, we are cos square theta, and here you will see the sin square theta lines, which are the right side, where you will see sin square theta lines. These are the arrangements of sin square theta. These are like these. Some of these line segments are collinear to the cos square theta lines. Now we have taken it nearer such that you can compare them. Let's see how good you can compare these line segments. Suppose the blue lines and green lines are kept at a certain distance, so that you can clearly see the line segments are addable or not. Suppose you have separately prepared the line segments of cos square theta and sin square theta, then you can easily check the arrangements are summable or not. See here, this is LBBZ, this line segment. Which of these sin square theta is addable with this? This plus this gives you the 1, that is the unit length. L is taken common, then cos square theta plus sin square theta equal to 1, that is equal to the length of the L. You can cross verify these things with this file, and you can follow the construction protocols here. You can download the construction protocols and you can check those also. You can download the construction protocol and you will get all these things stepwise there, and from that also you can check The 219 construction steps are done. From that you can see, I will play the construction protocols at the end of this video, and then you will understand the things there. Now start comparing these things. This line plus this line is equal to 1. This one is the different line, but this is a construction circle. I want to select this one is LHH line, or this one plus this line are making 1. So sometimes this line and this line and also this line are all collinear, and here two lines are overlapping. Only two lines are overlapping here. Here also two lines are overlapping. Here also two lines are overlapping. These two lines are both of length cos square theta, and this small part is also sin square theta. This part is also sin square theta. So one line ends before, one line is from here to here. That plus this one is equal to cos square theta plus sin square theta. Another line is starts from here to here, that is cos square theta, and this line is the complement of that, which is sin square theta. Similarly, here you can see a line is like this, and this line is from here to here, which is cos square theta. Then another line is here, that is a sin square theta. Similarly, we can see there are 3 circles. This one is a special circle. This red one is a special circle which passes through 8 of these points. So it is a 8-point circle. Here also this is a special circle. Both circles are of having same diameter. 3 circles are the controller circles. This is the inner circle and this is the inner circle, and these pictures are complementary pictures. This picture turns into this kind of picture for 90 minus theta. So both pictures are complementary. And I wanted to show the arrangements of, there are 16 varieties of arrangements of cos square theta line segments, and here you can see 16 varieties of arrangements of sin square theta line segments. This diagram continuously changes when theta changes. I will show playing the video with the simulator where every data will change, and then you will understand the nature of this geometry. First, I am trying to explain you that which kind of line segments are behaving as a complement to other. This one is the cos square theta line segment. This one is the sin square theta line segment. Both comes collinear and it makes 1. So there are different kinds of arrangements with which cos square theta plus sin square theta becomes 1. Now, out of these, when these 16 and 16 options are collaborated, then there are 256 options possible. Out of them, 64 are very good, almost collinear, and then we can add them. So 64 are special kind of Pythagorean summability. 256 are total possible Pythagorean summability, and total 2 plus 2, 4 are very well placed line segments which are addable every time and which overlaps on the original line segment L. All of the other summations are collinear, but not all lying on the same line segment, initial line segment. So returning back to the initial line segment is tough, and 4 out of 256 combinations, only 4 out of 256 combinations give us the perfection of Pythagorean summability. 4 divided by 256 is the chance of getting possibility. So 64 options are very unique. 1 upon 64 is the probability of getting perfect Pythagorean addibility of cos square theta and sin square theta. I wanted to show these possible options here. It will help you more when I will play it right now. First note that there are 219 construction steps I have used, and for a long time I was working on this such that I could develop this for you, and I have used JavaScript to manage it within 219 steps. Otherwise it could take more longer. It could take around 800 to 900 steps to construct this geometry in front of you. Now I will play this to show you the nature of dynamics here. See, all the angles will change, and from that you will see the geometry will change. The geometry will change. Here you will see the angles are changing, and here the arrangements are also changing, and it is tracing its data, and ultimately the cos squared theta arrangements are also changing, sin squared theta arrangements are also changing, and slowly it will change, and the configuration swaps. Sometimes this picture looks like this picture, and sometimes this picture looks like this picture. This green line is turned into hypotenuse, which was a 5-point conic, which has turned into a hypotenuse, and again it will become a conic after some time when the angle will fit in that right positions. You can see the geometries are keeping its traces, and from this you will study with your high potential computers with higher graphics. When you will check the same file in your machine with higher graphics, then you can see better outputs. This is the trace of inner circle. I have kept the tracing there so that you can understand it, and with these changes of configuration you will understand that all line segments are taking different positions every time, and the configurations are also changing. With this you can change the length to 1 also, so that you can check the visualizations better. You can see all the line segments, names, nomenclature, and construction steps here. That will help you to understand how this construction is done, not only for this theorem but for every time to construct geometry with GeoGebra. These things will help you. I'm stopping the animation so that I can show you the construction steps in this video. Suppose I want to zoom to fit, and then I will play this construction sequence like this. The 219 steps are done to construct this whole thing. Several construction circles are made, several midpoints are taken, several perpendicular bisectors are taken, several angles are copied, and line segments are added. Then again perpendicular bisectors are taken to generate the symmetries. Again construction circles are done. In this way whole constructions are done with 219 steps. It is not very easy for everyone to construct this geometry, to demonstrate all process of Pythagorean configurations in front of your eyes, so that you can see, at least you can see, there are possible 256 ways of adding cos squared theta with sin squared theta. Normally you will not get this kind of things in any websites or in any video yet. I claim that because I am searching this for so long time, so that I could see these without constructing myself, but I had to make it myself because I was not getting any such video in front of my eyes, nor I was getting any GeoGebra file, so I had to make it. It took time, and next video we will come with more detailed version of sin theta cos theta. There are 16 varieties of sin theta into cos theta and 16 varieties of cos theta into sin theta. These 16 are also not always matching, and you will see the interesting thing of geometrifying trigonometry, where the line segments represents number and numbers represents line segments. Ultimately, plus minus into divide are done through the similar triangles, and right angle triangles are also similar when theta are same, and when multiplied, the smaller triangle, bigger triangles of same theta where combinations are forming, which are similar triangles. So the gluing are done in that way. All squares, cubes, and other powers of trigonometric expressions are done. And if you study these files of GeoGebra, then you will also understand the construction protocols, how to construct things in geometry, how to reason things with geometry, how to verify the geometry problems with trigonometry, and how to construct trigonometry problems with geometry. Our mission in geometrifying trigonometry is point 1, to convert all trigonometry problems into geometry diagrams like pictures like these. Mission 2, we had to make a convention for naming every points and every line segments so formed when we try to draw the pictures of trigonometry expression. And mission 3, we want to generate several theorems out of these arrangements of line segments and points. And to do that, I had to make a parser which reads trigonometry expressions written in spreadsheet formula format, and then automatically to generate the javascripts, or automatically to generate these geometry pictures out of the trigonometry expressions, such that we can automatically generate several theorems out of the trigonometry problems in our school books. That will give us bigger insights and deeper insights to understand even the quantum geometry, because the four symmetry is common in geometrifying trigonometry and quantum geometry, and Jacobian identities are also hidden inside these pictorial arrangements. The Lie algebra are also to some extent available, but geometrifying trigonometry is associative but not commutative. To some extent, for some cases, it is not. .30 is representing a projection of a line, and it is also a line segment, so its length is half of the given line segment. That doesn't mean the cos 30 is a number. Cos 30 has a value, but that value represents the ratio of multiplication of a given line segment transformed into another projection line segment. Ultimately, cos theta shows a line segment on a geometry system. It is not a pure number. We should not confuse about that. That is the first concept we have to keep while we talk about geometrifying trigonometry or whatever about the geometry. Our fundamental need is to understand geometry as trigonometry and trigonometry as geometry. Thank you. We will come with the other videos of different trigonometry problems later on. With next video we will come up with sin theta into cos theta is not equal to cos theta into sin theta. Be with us and see different geometry constructions. And again, please see this video and see this GeoGebra file. It is more important to look at the GeoGebra file